Say share. What did I say? I would assume so, right? No, this one. I mean this one. Okay, cool. So back to the isolation mechanisms. So just a reminder. So we were looking at Intel memory protection keys, right? And so just like quick thing. So it's remember what I was saying. It's a key it's a tag in a page table, and there is a per CPU per core for logical thread register, which is called PKRU, and it holds accessible tags. So it's the program essence of it's one address space, one process, and you can split this address space into multiple isolated subsystems. Like for example, here is a domain A and domain B. They have two different keys, like pages, which represent the people of these domains, for example. And then when you're running inside A has to be marked as available, right? Just remind them. So the question is like, we kind of stopped, like Jared was asking, how do you pass things around? But just let's quickly remind ourselves. Remind how we can build isolation on top of it, right? So the idea here is the following. So if you have, wait, where is it? If you have two isolated subsystems, remember my story that you probably want to kind of like have sorry, maybe let's go here. So like if you have two subsystems in one address space, one page table, subsystem A and subsystem B, obviously, if you're running inside A, which is blue here on the screen, the value of PKRU will have this combination of keys. The blue will be available, and supposedly you say you have a region of memory, and that's related to question to how you pass things around, which you plan on moving into B, right? On a cross subsystem invocation, right? You will designate an individual key to that region, right? And inside green, obviously, if you're running inside green, your key will be just green for now, right? Because green doesn't have access to this, to the brownish, orangish region of memory. And then if you say, look, I'm trying to pass this region of memory between the subsystem on cross subsystem invocation, kind of you invoking a function f, which sits inside B, then you essentially, your like here, your piece of trusted computing base, however you implement it, will update the key of the green subsystem to include this orange object as well. Is it clear? So what I was trying to explain, it's probably not clear. So what I was trying to explain is that today we have enough colors, which is amazing. Although this is also green. So if you're sitting inside the isolated subsystem, which is green, your PKRU will have a tag of the green one, right? So your PKRU will contain the tag of the green one. If you don't pass anything between, right? Remember our move semantics. When you invoke a function inside another subsystem, let's say it will be blue. We don't have blue, we have. Last time there was blue. They used all the blue. Let's say it's white, right? Then you simply will, when you do this function invocation, essentially remember like we talked about the trampoline, it was something like write PKRU, and you will write something like white into it, right? Before kind of calling function f, right? So essentially you're changing this from being green, the tag will now be white, right? And the question is like, how can you pass something across? And I don't see an immediate way for how it can be done besides this scheme where you say, look, all the objects which I won't be able to pass, like in my story, it's an orange object, will have a designated like key. So essentially you say it's an orange tag. And originally that subsystem will have two tags, like its own heap is green. Remember my story that you typically have this separation between your private heaps and your exchange heap, and then this picture, this object, which I'm planning to pass across, is on the exchange heap, right? And my private heap, all the green objects, they will always stay green. I will never be relabeling or passing them across. But essentially then, you say, look, when you switch from green to white in my figure, and you're passing the orange across, you allow the thread which is running inside the white to have not just the white tag, but also the orange tag, which means that if you pass the pointer across, this pointer is valid and can be used inside white, right? This is kind of a zero copy, right? I didn't copy any memory, so this region can be large. It was passed by just updating the flag, by updating the tag. It's also move semantics, right? Meaning that if we trust the TCP, which implements this code, then we know that green one lost access to the orange one. So if the green tries to access it again, it will not be able to do so because this tag will not be restored, right, on the way back, unless the orange region is passed back to us, right? So there will be no time of check, time of use attacks because the white subsystem here will know that, okay, it's the white is the only subsystem at this moment in time which has access to this orange object, right? So that makes sense. So we have a couple of useful properties. Zero copy, meaning that we can pass objects very, very fast. So we didn't if we don't have this, then we would have to create a region of shared memory, again, designate a tag. I don't know, I don't have a color here. Let's imagine some other color, and then this tag 3 would be enabled when both these subsystems are running, right? And then, or alternatively, since we can control the page table, we can map. I was thinking mapping to the physical memory twice with two different tags, but it's really backed up with the same physical memory. So it's a shared region of memory, right? So you can do that as well, I think. But then in order to avoid time of use, so then you have to copy into the shared region. And if you want to avoid it automatically shows up here, or let's just go with the simpler idea of a shared region, which is shared between the two subsystems. You copy the object into the shared region, but if you want to avoid the time of check, time of use attacks, then you have to copy it out, right? So you spend some time doing that. But if you do zero copy, then you don't have to do any copying at all, and you have move semantics, meaning that it solves your time of check, time of use attacks, right? That makes sense?
The orange one is not shared.
Yeah, it's not shared. It's moved. I use move, but it's easy to understand for people who do Rust, but it's kind of like single ownership. If you have a context of execution, you have a pointer to an object on a heap. Rust has this guarantee when you can move it into another context of execution. You can think of it as a different function or maybe a different thread of execution. And then the original thread loses access to this object. In Rust, it was designed this way to prevent data races, because you don't have a race if you don't have a shared state between threads, right?
Yeah.
So that's kind of clever. But in security, the same kind of concept comes back to you and says, look, shared state is bad because if I, for example, start reading this state, checking for some properties of the object, maybe it says, okay, maybe the next field means something. And then attacker sitting in another subsystem concurrently modifies those fields. Then you can get into inconsistent, you observe inconsistent state, and you can trigger different, either it's really different behavior, semantically different, and the program just does something what it wasn't supposed to do, or maybe crashes, right? Or it just does some kind of a semantic exploit saying that instead of charging you $1, it will charge you a cent or something like that, right? Which is an attack. But moving means that the regions on the exchange heap are always uniquely single owned by a subsystem. And this is a nice property. So Singularity was doing it, Rust does it, but for concurrency reasons, Singularity was an operating system written in Sharp, and it's like enforces this isolation property for reasons of fault tolerance.
How about the green subsystem have another key to with another subsystem?
You mean like imagine it has another object on an exchange
Yeah.
heap? Well, then it retains the tag to this object. Let's say it's tag 4. Then this tag 4 will, when you context switch back, when you return from this function invocation, imagine white doesn't return the orange one back, but green was still there. So you will be running back with your green tag and the tag T4, right? So you retain your state, right?
So the blue one cannot see the green heap, right?
Right, cannot. That's like, it's like two different processes which are isolated, but they live within one process. It's in process isolation. They live within the same address space, but have completely isolated state. And can pass object across saying, okay, I'm like, you can think of it as a browser extensions and you passing parts of the, I don't know, DOM tree is a little bit involved because you may say that if you have a tree on the heap, every time you pass it across, you have to check that it's well formed and those pointers do not point nowhere or something along those lines. So the checks become complicated, but if it's something semantically simple like a buffer, then it's totally feasible. It can be a network function or it can be like network functions which process packets in a chain of network functions. Question.
See, the function has some arguments to accept. So the green one will push the arguments of the heap, then we call the function that nothing.
We can, but remember last time we said that we can also come with some application binary interface or a calling convention, and we say that maybe we'll pass some number of scalar arguments in registers to save and some larger stuff on the heap. And so if you don't fit in registers, then you'll still on the heap. And you can design different schemes where you say, look, well, I might always have some small shared region of memory to pass, let's say 32 scalar arguments or something. And then you just copy in and copy out. But that's okay because they're like kind of like small. It's a little bad because if you have a multiple concurrent invocations in flight, you always kind of like, but you can also come up with a calling convention where you push those arguments on the stack, you jump, instead of jumping immediately into the call-e subsystem, you first jump into the TCB, trusted computing base. And supposedly, maybe this jump is reasonably fast because your hardware primitive is like just a couple of cycles. And then this TCB maybe like will be copying from one stack on the stack of the calling, but that's a little funky because typically you choose the stack of a calling only when you reach the calling from the linked list of stacks, for example. And then by then this stack becomes unavailable because you're already here. But maybe there is some kind of a trick we can come up with, like copy into some intermediate state, but it's double copying, so you want like to avoid it. So ideally, yeah, stick to registers and maybe some objects on the exchange heap. There is a couple of unpleasant surprises here. So who can point me a couple of limitations of this scheme? Who was listening carefully? What's the limitation number 1?
If in the future some new subsystem wants to access the shared heap, no.
It will not be able to do?
Well,
Maybe it will, why not? If the runtime allows you to load a new one then and connect it, that's probably solvable. There is like a couple of hardware limitations of these mechanisms, which are kind of ugly. Limitation number 1. So who can tell? Someone? Jerry, you will be a volunteer. Correct. We only have 16 tags. In fact, tag 0 is special, so we have 15 tags. Right? You see? Because I said the tags live in the page table. In the page table, like I made the page table, like, you know, it's not the picture, but it's a hierarchy, and this is the last leaf, and there were only 4 bits available because all other bits are used for some reasons. And so 4 bits and code 16 tags. What if you have, and moreover, like one subsystem takes a tag, right? And if you have some objects on the heap you want to pass, in my zero copy scheme, those also have a tag, and you can only have 15 total. In practice, it means that probably you cannot build much with this mechanism, right? 15 total, it's either 2 subsystems and what, like 13 objects on a heap, or maybe, but like it's such a stretch, right? So that's limitation number 1. So 15 tags. What's limitation number 2? Kind of ugliness, which is hidden a little, but is also hidden. I'll erase this while you're thinking. Any ideas?
Will the reuse tag introduce any problem?
Well, you can virtualize tags. Not surprisingly, people started writing papers about it. It's horrifically slow. Because you have to to virtualize, you have to really change the page table that you can only do in a kernel and produces overhead. Like the second limitation is a little non-trivial. Imagine you, I'll change the drawing differently. So now this is like 2 CPUs, 2 different cores. And imagine this is subsystem A, and this is subsystem B. And you crossing like that from A to B, trying to invoke F, right? And you say, look, I'm passing you an object, a green object on a shared heap, right? So you're passing it here. And obviously, the PKRU register on this core allows you to access this green object, as well as all of the white or B heap, right? But what happens to other cores? The way we write programs, if we pass like a pointer, we can imagine that if there is another thread running here, it also wants to access this pointer and tries to access this green object, right? But on this CPU, we don't know anything about this PKRU change. Because inherently what we've done, we pass the object by updating the register on the CPU. Any other CPUs have no idea that we did it, right? And there is this mismatch. So if your code, which you write, for example, C or Java or Rust code, it assumes that if this pointer somehow synchronized to this thread, maybe it's not even instant, maybe it takes like seconds. This might even exit back, but the green SKU was passed to this subsystem, right? There is really no way for other threads to know about it, right? Agreed?
I think we talked about this, concurrent CPU core of this.
Yeah, I said core coherent synchronization of writes. Somehow, my surprise was that this concept of core coherent synchronization of writes is nowhere kind of on an immediate radar of those designers of isolation mechanisms. They don't talk about it. There will be in the last 10 years, you will find dozens of systems which do not satisfy this property. Yes, you can write single-threaded workloads, but nothing. It doesn't help you to really build real software which is multi-threaded, right? So that's nowhere around. So I don't see there is no core coherent passing.
No one works on this.
Huh?
No one works on this code.
Well, I'm pretty sure that you're never like in a vacuum, so I'm pretty sure that someone is thinking about it, but there was a bunch of papers which omit this limitation altogether.
Is the problem is in the last area?
What?
In the last, how does last area?
How does Rust handle it? Good questions will be answered.
I don't know much about this.
Yeah, we will have a lecture on something about it. It will be about my Bradley grading system, which uses Rust as an isolation mechanism.
Oh.
Jafunk is a co-author. So it's his as well. He built parts of it. But no one knows the answer. The thing is that Rust itself uses language level isolation, meaning it trusts the language safety, meaning if I say that the field is private, there will be no way, like, essentially, imagine you have two modules and you say, look, some private fields point to some objects, and there is no way to like, for this module B, for example, to access those objects, because there is no, in Java, there were like introspection mechanisms, and you can access everything from like some root object type, I think. In Rust, it doesn't exist. So if you're running inside B, you can only access what was explicitly passed to you through like some kind of a communication channel, which means that this guy A put a pointer to an object on a heap into the communication channel. B popped the pointer maybe in its own private field, right, at the level of a language, but its hardware is not involved. And then this pointer can be used by B, right? And since it's just a pointer, if you have synchronization mechanisms between two threads, T1 and T2, then this pointer is available like as a regular pointer, right? So language does it slightly differently, but here we rely on hardware. We run any garbage generated in any, compiled from any possible language, maybe it's C, maybe C++, maybe even Rust, but we only trust the equal protection keys to implement the isolation boundary, right? But we will get to languages. So it's nice to have this language-based isolation, because I think it's not that it might be one plausible future in which we're moving, like using language-based isolation. I'm not saying that the problem is solved. There's a ton of different like kind of problems there. The major problem is that trusted computing base of a language is giant. You trust the compiler that it compiles the code correctly, trust the semantics of the language that it actually like implements those private fields correctly, and there is no kind of someone just forgot something and it's suddenly unsafe. In fact, you like in Rust, there are unsafe extensions which break isolation, but we might get there eventually, right? So we'll talk how to even build such systems. And Singularity there was a line of work obviously before Redleaf. Immediate predecessor is Singularity. And as I was mentioning, there was Coffee OS, which is from Yuga as well. And there was like J-kernel. I think it's maybe kernel or something. So we'll get there. But okay, is it this Intel protection keys are clear now. So we have two limitations. And there is like, I have my own suggestions in the paper for how to solve them, but I don't think that it can be easily solved. So I think it's a research challenge right now, right? Okay, so cool, but we at least understand them. I wanted to just, so this is how we pass. I wanted to just come back to, I wanted to come back to one thing, but we can come back to it probably later. Okay, our next mechanism is something what is called ARM memory tagging extensions. By the way, Jafang just told me today that ARM also now has, in the most recent version of ARM, has something what is very similar to Intel memory protection keys. What is it called, Jafang? Permission overlays. You see, I didn't know that. So I don't know how they work, but just make sure that you remember that maybe there's something. So, okay, but ARM came up with a different scheme, which is also mind-blowing in some ways, because they say the following. If you want to do like a memory load or store or some kind of a memory related instruction, you obviously will pass a pointer, right? And they say, look, since, the upper bits of the pointers are not used. So we will put a tag there in the upper bits of the pointer, which means that you might have a ton of pointers all over the place in your program, right? And what happens next is that, by the way, somewhere hidden from the program in memory will be a table, and it's called permission table. And each tag controls a 16-byte region. Essentially, you have, let me draw it differently. If this is your virtual address space, imagine there is like entry number 0 and entry 16 bytes, right? There is somewhere a table hidden from you in memory as well. And this first entry controls the tag for this address, right? So it's one-to-one correspondence. So if this is like 55, there will be like entry 55, which will control the tag, right? And so if you're using a pointer, which has some kind of a tag here, right? And you're trying to access this memory location, 55, for example, the root value will be 55 here, then the hardware underneath will look up this table, which is hidden the permission table in memory, and we'll check whether like the tag here matches the tag of the pointer, right? If yes, then the access is allowed. If not, then it's an exception. Agree? Right, so here we go, like, so essentially address points like leads you to a tag table, you compare the tags. The question is following. If you wanna isolate something, how will you do it? How does the isolation work with this mechanism?
We can like move it. Like tag.
We can, but let's first talk about. I'll erase, like, let's even implement private keys. How can we build private keys? Go ahead, Jared, tell me. Good.
We assign different tags for each private process.
It lives within a process, right? So let's call it isolated subsystems, right? So parts of the process. I just want to like kind of make sure that we understand how it works. We patch the malloc, for example. Malloc is part of our TCP. But when we say allocate something from within the A, right, it returns us an object, right? And obviously it will be marked. I will put a tag here, A, but like the tag will live in the table, right? Agree? Right? And so on, if we allocate a bunch of those, right, we do mallocs or whatnot, like we have all of this all over the heap, right? They will all be tagged with A, right? Which means that we can access those objects, right? And similarly, if we like invoke malloc within B, we will get the heap, which is will be marked with B tag, right? Agree? There is a little wrinkle here. Since we're programming in unsafe C, what prevents an attacker from overriding the tag in any of the pointers and immediately accessing these objects? Huh? Nothing. So how can we do it? How can we solve it? But you got the problem, right? It's whatever. You can, like, it's C. You can typecast any integer value into a pointer, which means that you can like put any value here. You can come up with other attacks which just overflow something and spill into the tag, right? If you're more sophisticated. But really, the tags are not protected. They are just live on every, what is this pointer? It's part of some data structure. Of course, the data structure was allocated from malloc to begin with, or maybe it's whatever, global, it's marked with A, and you also put a pointer which says A as a field of this data structure, maybe it's field, I don't know, X, for example, right? But nothing prevents attacker or untrusted code from like changing this from A to B and changing whatever the field, like address field is, and accessing objects of a different There is no key in the hardware, like it's all, this is what's going on. So hey, what's the solution? How can we solve it? Then Jerry knows the answer. He doesn't.
I think.
You marked what?
You mark the.
No, there is no like marking. Hardware doesn't support it. It's just like you can, like, it's literally a load and store instructions. And you say, look, there wasn't a value. I got it from the register R1. Whatever was in R1 contained a tag, which I will follow. Right? But there is no protection for tags or anything. Okay, an obvious answer. Shafang knows the answer, but it's not fair because he wrote this paper. Right? So again, remember my software fault isolation from last week. We did a pass enforcing the bounds, right? On like essentially compiler pass, which was saying if address inside R1 is in bounds, then yada, yada, yada. We allow the access. If not, we panic. So here we do a similar trick. We just enforce the tag. We reserve yet another register, whatever, R32, for example, or how many registers ARM has. And we just do some kind of a bit masking operation saying that whatever R1 had in its top bits, just take it from R32 and it's A and overwrite it right here. And this way we know that this access will always be, no matter whatever the attacker change it to be, in front of every load or store, we will have overwritten it back to A. Agreed? So then it works. So it's a combination of a hardware feature plus software fault isolation pass. And it's easier because it's like, it's not about bounds. Our heap is more kind of like, there is no strict separation between exchange and private heap. In fact, you can send any object across, or if you want to pass it inside F, your TCD will just like happily retag like what it does in that permission table, which corresponds to this object A. So it will change A tag to B, and then this object will be accessible to B, right? At this point, right? Agreed? It works, right? And it's probably a little bit faster than traditional SFI. Why? I mean, first of all, maybe there's a one bit operation instruction that's kind of very similar to SFI pass, so probably same performance. But the benefits which you gain here, you have zero copy passing of objects because you're updating the table from A to B, right? And it's zero copy. So this object can be arbitrarily wrong. Oh, not exactly. So if this object consists of multiple 16-byte regions, so you have to retag consecutively everything from A to B, right? Because this is how MTE works, right? So zero copy is there. That's nice. You can pass anything. As a system designer, I recommend you to pass some very simple objects because if you pass something recursive, it gets a little ugly because then your TCD has to walk this hierarchy and retag B and who knows what. It's doable, but it's not fun. I did it myself. I mean, I will talk about the system which does it, but for backward compatible reasons. But if you build clean slate, passing complex data structures will lead you to multiple attacks. So it's a little tricky question.
Okay,
Okay,
so let's say I have a pointer, say it's like a use after free time, I have a pointer. But it's been, but like the tag's been changed. Yeah, so like there's nothing stopping you from guessing, but it's like 4 bits.
Correct. So what you're saying is the following. So
And I know you
wait.
can't-
Wait, hold on. Maybe I misunderstood the story. So imagine you starting the pointer to A, right?
Yeah.
Because like you cannot use any inside A, you cannot use any other tag. It's the tag is assigned to you. It's not secret, right?
Yeah.
But even if you stash a pointer, and later on this object was free and
Oh, you're using this in the just isolation.
Right, but wait, what is your question? Maybe, even if it was reallocated to B, because you freed it, it's used up for free. If it's used up for free and it's unallocated at all, maybe this tag is like some random unused tag, then you're gonna crush, and it's an exception. If it was out reallocated to B, you still crush because it will be marked here in the permission table as belonging to B, right? Agree? So then it answers everything for you?
I guess I'll just again, the context. Not like using presentation, but just to use it for text. Use that for free text.
Right, no, user for free is a perfect example. And I think, in fact, ARM was designing this mechanism as a hardware support for lightweight address sanitization. So you can like catch those safety issues early, because if you say, look, if it's user for free, the moment it's free, you change the tag and then you catch it, right? And then maybe later on you will get allocated it again, and then you will not catch it, but at least you will catch some subset of bugs, right? And that's nice. And then you don't need any SFI. Maybe you just trust your code, right? If you're accessing past the buffer, you can also catch it because you can implement a canary beyond the buffer, right? You can, like, for example, randomize the tags and say that my memory allocator will be like randomly like choosing the tags. And then if you, through the point, you trust your code to not override the tag, right? And so you say it's A, and I'm trying to access the object which was allocated as A, but I go out of bounds, and then you hit B, and then you catch this out of bounds access as well, right?
So if you want to move, you can change the tag.
Yeah, if you want to move, you just change the tag, so that works. But yeah, it's amazing. Wait, hold on. So like Jared is jumping ahead of the horse. He's saying, okay, how will we move these objects, right? Well, simply you say, if I want to send this object from A to B, I will just retag the table, right? And by the way, it's core coherent, right? Because if I do this on two different cores, right? Like if I did a load instruction, like if I pass the pointer and I do the load through the same pointer here, supposedly the hardware is designed such that it will fetch the value of the tag from this table, and coherence is implemented. I assume, we don't know for real, we didn't do the checks with ARM. Maybe it's broken, maybe there is a window of time, but yes, it does work, right? So it seems that this scheme does provide support from zero copy and core coherent synchronization of writes. Agree? What's the main problem with this scheme is that it requires an extra memory access. So imagine you have a large address space, right? And now instead of and you accessing in a random fashion, it's a hash table. You access it, this object and this, and it's all over the place. Of course, the smart CPU designer will implement some kind of caching protocol for those tags, but if the address space is large enough, you always incur the second access, and instead of accessing one memory location, you're accessing two, one for the table, one for the object itself. You say, well, those accesses are in parallel anyway, so is it really, does it hurt you at all? It only probably hurts you when you are saturating memory controllers of your system, meaning that you may be doing linear scans, or maybe you're doing database joins, and the algorithm is so optimized that you fully saturating the channel between the CPU and the memory, right? I have a paper which does it. It's called RAM-HIT. It stands for DRAM and then HIT, meaning that we design a hash table which essentially just saturate the memory controller. So if suddenly you, instead of doing one cache line accesses for each memory access, you do two, performance of this system immediately drops by half. That sucks, right? That's main limitation. What are other limitations? One shared with the previous. mechanism. Same as above, I will write in my paper. No. It's cliche. Okay, who knows the limitation?
Explain it.
There is nothing to explain. I'm asking a question. What's wrong with this scheme? You say you love it, so you tell us that. Then you don't see any limitations. Then argue and tell us why is it so good? Why you love it? You love it because it's core coherent and it has zero copy. I agree. I love it too. Yeah. But what? Correct. Still 4 bits attack. So we only have 16 isolated subsystems. Although now we don't need a designated tag for each individual object on a heap because it can be shared with the heap of the subsystem and then just split, right? But we still only have 16. And conceptual limitation is that we only have, like it's in a pointer and we only have so much space in the pointer. In practice, I think we can do the pointers on the ARM allow us to at least double the space or something along those lines. So it will be not 16, but what is that? You have to power of 2. What is that? Like it will be 256, right? I would assume 4 and 4, 8 bits, right? So, but still not a large number. Although 256 maybe practically is okay, right? That's one limitation.
It's part of
Right.
64-bit backups.
Yeah, so like on ARM, on 64-bit systems, the pointers are only like, let's say 56 or something bits. And the upper bits are always 0. So like used for some other purposes. So they are available. And this is where the tag is stored. And all the like pointer copy, everything operations propagate the tag because that's part of the 64-bit value, right? So the second limitation, like first one, 2 accesses per DRAM access. Second, limited number of bits. It can be probably solved by introducing how can we by keeping the tag. Let's first do the second limitation, the third limitation. The third limitation is this SFI pass, this bitmap operating instruction, which we have to insert in front of every load and store. I will, in about like, I don't know when, like in hopefully today, 10-15 minutes, I'll show you the performance overhead, but it kind of sucks. It kind of brings you back to the overheads of SFI, which I discussed last time. And that's like, Jared, I think this is like, if you say, wow, you rarely see workloads which saturate the memory bus, the fact that you have to do an SFI pass and lose between 10 to 40% of performance essentially makes this mechanism impractical on modern CPUs. One solution, how can we solve it? Like as a CPU designer, how would you change the scheme to make sure that you can avoid this instruction in front of every load and store pretty easily? You don't know. Man, Rajiv doesn't teach you well. Look, you say, look, instead of keeping the tag in a pointer, we will introduce a per CPU tag register, TRAG. And this tag register will keep the current tag. And then this is the tag. Instead of picking up from the tag from the pointer, you will pick it from this register and resolve it against the table. Then you don't need this instruction. No matter what attacker puts here, we just ignore it. We'll always take it from here. And only when we switch domains, we will update the tag register. The move semantics will fly because we will, when we switch between the domains, we will retag the permission tag for the object on a heap, as well as change the per CPU register tag. And coherence will stay because if on another CPU, you're also jumping from A to B, the TRAG will match for B, right? And then it solves this, like the whole business of SFI kind of like easily, right? And it gets probably pretty close to this, the mechanism which is acceptable, but somehow they didn't figure it out. I would, if you do it this way, probably the performance overheads drop to nearly zero and everything is kind of flying. Besides the workloads which saturate the memory bus.
I guess.
Say again?
One reason it wouldn't implement that though is because like if I thought like the way MT basically works. Let's say you're not doing any of this sharing or.
Yeah.
System, I thought like every time you would valid, get a pointer with a random tag.
Mhm.
So you wouldn't have that.
Correct,
But in this situation, that makes a lot of sense.
correct. And
You
they,
probably do both.
I think, yeah, you should probably do both because then you can use this scheme to do this address sanitization, kind of random tags, use that for free attacks, or do the change of a hardware tag to make you sure that you fly fast. Okay,
PKR register.
yeah, PKRU, like I called it tag register, but yeah. Okay, cool. So we looked at this. The next one is, wait, what is it? What is it? Isolation was MT. Like, yeah, tag, compare the, this my SFI pass on the slide, enforce the tag, then load, right? I don't know, like it's just the same stuff which I already explained. Next scheme, although I guess people are getting tired eventually from those schemes, but let's just quickly look at it. So I'll just glance at it. So it's called ARM pointer authentication. This gets even crazier slightly. So essentially, again, top bits of every address. Oh man. Probably, I don't want to. I mean, I don't think that you guys care that much. I don't know, like to listen about pointer authentication on ARM, because it's a slightly even more exotic scheme which allows you to sign pointers and then build kind of like different things. But the reason it's less important is that it's more complicated and it's less, it introduces higher overhead. So probably like if you're gonna work in this space and start working with this pointer authentication, you can probably look at it, but I don't want to like torture you because probably it's just totally fine to essentially just keep it for now, because you know the slides for PAC gets like this is how it goes. You need like a metadata table, yada yada yada. So it will take you forever to figure it out. But what I wanted to kind of like go to, which is slightly more interesting, is something what is called cherry capabilities. So in some way, like this ARM pointer authentication is kind of cherry capabilities in software, but a team from Cambridge figured out, and I mean, it's not a new idea. So there was a very huge line of research which said, okay, so what if we want to build a piece of hardware which kind of does the same trick, but protects the pointers in hardware? So in my explanation about MT, I said that every pointer will have a tag, but in order to protect this tag, we need like an instruction in front of it, because literally there is no way for us to protect the tag, right? So the attacker can just simply load something into this tag and just change it from A to B. So we will enforce sanity by overriding with a specific tag number which corresponds to this specific subsystem in front of every load or store instruction, right? But what if you imagine the hardware which actually does protect this tag? Like somehow in hardware, you say, look, you have a pointer, and moreover, like instead of just keeping the address of the pointer, which points to like object on a heap, the upper part of the pointer will also somehow contain the bounds, meaning that, first of all, if this address goes out of bounds and you're trying to access past this object, you will get an exception, right? But also that you cannot change those bounds. So no matter what you do, you simply don't have access. Like this tag, but protected by the hardware. There is no instruction which reaches into the upper part of the pointer, and hence it's protected from your program. So the memory allocator, which sits inside like some privileged execution mode can change those bounds. But your program cannot, because like allocator has a privilege because it runs at some privilege level, but everything else cannot, right? And then you say, look, then maybe my problem is solved. So essentially, I have my pack-like or MTE pointers in which I say, look, I really can construct those heaps where, like subsystem A is isolated from subsystem B by merely the fact that, they will never have overlapping pointers. And there is no way to make up this point, because the only way to receive the pointer with valid bounds is from a trusted part of the TCP. And this is like, I forget exactly how Morella codes those privilege levels, but maybe this is called executive mode. And I forgot what the non-executive mode is called, right? In executive mode, you can manipulate the bounds, like can invoke instructions which manipulate the upper part of the pointer. But in this non-executive mode, you cannot. Hence, you cannot make up pointers, right? Makes sense? But isolation flies. So it's kind of like, it's a little like, I don't think it's super easy to understand how you can build isolation with Morella with Cherry capabilities. But if you already familiar with this idea that, you have isolated heaps, and you say, well, this is objects belonging to A, all the pointers which like allocated to A will have correct bounds, and those are objects allocated to B, they also will have correct bounds, and the only way is to essentially pass the pointer across, and then B will have an access to this object, right? Agree? So I just emphasize the fact that this Cherry project, it's extremely mature. So one of the creators of the project gave a lecture here, I would say in 2013 or 14. I wasn't a student, but I probably was like a research faculty here, and I met them. And I mean, it was a great talk, but it's been like, what is it, like 10 years ago? And today they actually have an ARM silicon, so like not some bougie FPGA implementation, but a real ARM silicon which comes out of an ARM factory, so it's reasonably optimized. And we actually have a box in our lab, right? So it's kind of like a project which was pushed far for many years. There's like 2 chains. Okay, what needs to be done to your program, right? So let's answer these questions. One interesting thing is that now suddenly, if you had a data structure which contained a pointer which was 64-bit, now you somehow have to change the type, and this has to be not 64 bits, but 128 bits. Sometimes it's almost transparent. You just say, look, wow, I'm like, it's so easy, a compiler will do it for me. But if you rely on some kind of like packing of stuff, meaning that maybe you're building a hash table, you calculated that some number of values fit in a cache line, suddenly everything breaks and only half of them fits. So sometimes it's a little less trivial. If you have some assembly code which manipulates the pointers, I think there is some kind of a backward compatibility mode, but I don't know about the details, but there are some like software changes involved, right? So that's challenge number 1. But otherwise, it seems like an ideal solution, right? Or not right? I will ask you again. So what's the limitation of this approach? What? Well, you said, but we can address it. So maybe, and Cherry Morella Cherry has a compiler toolchain, which will, I mean, Zhafang has a first-hand experience. So some things are easy, I would say, and some are nearly impossible because you have to hack through so many things where you like, typecasts and everything. It's like you typecasting to int, but now it's not an int, it's something different. So some things we are able to get running and some were hard, if I understand correctly. But that's not conceptual. Maybe with better compilers, everything will be just fine. What is conceptual here? What are the conceptual limitations of this system? Let's take a look at how beginning. Is it core coherent? With passing of rights, you can tell. Meaning that, remember my story about core coherence, which is if you passing a pointer on one thread, T1 passes like to the same thread, maybe this thread is migrates here, and passes a pointer to an object which is now like this object, label it green. What if there is another thread running here in T, which we will call T2, which runs inside B? Can it access this object? Yes or no? Let's raise our hands who say yes. Who says no? Abstain. Will you say no? Okay, you talked it up. So you say, why you say no?
Well, I was just thinking that since like everything has like bounds anyways, like the other thread, unless it was given I don't know, I was just thinking, but like unless it was like given that like bounds, it can't really like
Access it.
access.
Yeah, but hold on. That's the whole point. Cherry works. So like forget about isolation. What happens with those pointers when you're simply running two threads in a single address space? You're not using Cherry for isolation, you're just using it for whatever reason. Like if you have a pointer with bounds and ever to an object, the hardware is like if you save it in memory, like maybe in a cache, like in any memory location. Actually, Cherry, I forgot to mention, it requires some support from memory because you have to save the bounds. When you save the capability in memory, so memory has to like hold the bounds as well, right? But imagine you saved it to memory here, like in custom, like maybe you acquired a spin lock, you save it to memory, release the spin lock, the other guy says, okay, I was gonna acquire the same spin lock, load this pointer, it will be loaded with bounds and errors, and so access is allowed, right? So I just wanted to make sure that we understand that it works this way, right? And so in this case, if you're passing from one core, these guys either blindly read the pointer or maybe use a spin lock to synchronize the access, then fine, yeah, this pointer will correctly work in the thread too. So it's core coherent, right? In terms of passing. And it's zero copy, obviously. You simply pass the pointer. Agree? That seems to work. Zero copy is there. Coherent access, coherent passing of rights is there. Then what doesn't work? Who's listening? I know that I can bore anyone with this lecture at this point, but it's kind of almost there. What doesn't work? What about those time of check, time of use attacks? Which I was kind of in my dictionary, it was called move semantics. Is there move semantics on Cherry? Yes or not? What does it mean move? When A passes a pointer to B, A loses access to the object on a heap. Does it work this way in Cherry or not? Does A lose access to this object O1 or not? Not, right? Why? Well, like I would explain it maybe slightly simpler. I would say, look, nothing prevents a subsystem from stashing a copy this pointer or saving it somewhere in some kind of array, right? And still having it. Why not? Right? It passed the pointer, but like it can have infinite number of copies of this pointer, right? Which means that it will have access, and there is no way for B to trivially revoke those pointers and validate that somehow. Which means that like I can pass an object from A to B, but I cannot guarantee move semantics. More generally, this move semantics is related to the concept of revocation. Meaning that if I gave you a key, I want to have a right to revoke it, meaning that, and by the time the operation is done, I know that you don't have an access. It's very hard in Cherry. So Cherry suggests solutions like scanning all the memory of a kind of linear scan with some maybe hardware enhancements to identify capabilities with a specific bounds. It's kind of ugly. It will take forever to scan, right? But they do, that's really, they publish at least 2 papers, but maybe have even more, like advocating for this, right? But really there is no revocation and there is no move semantics, right? Because remember in a CL4 microkernel, how a revocation was built. Remember, or you don't remember because I didn't assign enough homework to remember, but in a CL4, every time you pass a capability to an object, remember there is this idea of capability derivation tree, but it's in software. So we literally maintain a list. So kind of like, if it was original pointer, we copy the pointer, there will be a linked list of all the copies. And if you say revoke, you can say like, okay, you know where to go and invalidate those pointers, right? In a CL4, revocation, recursive revocation is here. So no matter how many times you save it or do something with this pointer, we have a recursion and keep track of like how, like, keep track of all instances of this propagation of this capability. But here is nothing like that is there. So there is no recursive revocation. And arguably it's almost impossible to build, right? And because its hardware has to be fast, like maintaining the list for every pointer is a suicide, right? So I kind of claim that that's kind of like kills Cherry on arrival. So it just like it validates the whole point of this system for the purpose of isolation. It's again, it's a very glorified address sanitizer, or like kind of allows you to catch some safety bugs, or maybe significantly complicate the fact of exploitation, because you simply cannot overflow the pointer and access a different object. Now you have to do something smarter, but attackers are smart. And what really we can do is that we can like use some kind of like, of course, the window for attack is smaller, that's for sure, but you can still use semantic vulnerabilities and say, look, I pass you A instead of B, and you didn't expect, and at this point, maybe you crash, or maybe you send me a key. So the probability of this attack is lower, but it exists, right? So, right.
So does it support the shared memory? Let's say subsystem A and B as a shared memory. Is it possible there?
Totally, like just like in fact, this is shared. The moment you send a pointer across, if A retained a copy, then of course it's shared between A and B. Right? Nothing prevents A from losing the pointer. In our wonderful paper, we explored a technique in which we did a software fault isolation pass, and every time a capability was saved in memory, we constructed a data structure which kind of tracks where it was saved. And when it was passed across, then we invalidated all the memory locations, kind of revoking the capability. I'll show you in a second. Obviously, it introduced non-trivial overhead, right? To the point that Cherry, like again, slower than anything else. Tell me.
Is this overkill?
An overkill to demand time of use?
Yeah.
Demand.
I mean, I can start.
Right, but back to your wonderful user for free attacks. Cherry doesn't like protect against them. If you free a pointer, like imagine you're like a greedy attacker and you like stash pointers to everything you've seen in the past. Presumably you will have enough pointers to cover half of the heap at some point. And then those objects do get allocated for other subsystems or for something else, and you have access to them because the bounds are valid, right? The question is like, do you need isolation, or what is it you need? For that, I don't have a good question. So I only teach isolation, right? That's what you need. I mean, like a security researcher will tell you that maybe like Cherry positions itself as a safety for unsafe languages, right? Because roughly speaking, what is safety? Okay, who can tell me? In a safe language, what is safety? Well, there's like a triple of things which usually people say. I'll say one. It's called type safety. It means that if you access something as a type A, it really is a type A, right? Not type B, right? And the language guarantees that you cannot just simply like typecast one pointer into another types, unless you have some kind of like escape path, which typically exists in those languages, but imagine it doesn't. So type safety, memory safety is type safety, spatial safety, meaning that if you're accessing an object, you access it in bounds, right? And the third one, type, spatial. Third one can be guessed from a second. Temporal, exactly. Meaning that if you're accessing an object, it's still alive, right? In the garbage collected language, it's always like that because the garbage collector scans the heap and doesn't deallocate it. In a language like Rust, it's a little bit funkier, right? But now imagine Cherry. So Cherry, well, they don't have types. Well, no type safety. They do have spatial safety because there is bounds, but even temporal is kind of there. Their linear scan says, okay, we will only deallocate objects after we found the fact that no one accesses them through the linear scan or something along those lines. But really, it's kind of a stretch here. Nevertheless, I agree. As a security researcher, one can argue that, it significantly complicates the line of attack. In fact, one of my wonderful projects, which I wanted to suggest as a project for this class, is to take the list of vulnerabilities, let's say in the Linux kernel for the last, let's say 4 years, and think of how many of those will be eliminated by Cherry. And also maybe think whether they are exploitable with, I'm pretty sure people are doing this already. I didn't follow the discipline, but we did it for us. So like Zafang, myself, Jerry, we did a paper just recently. We say, imagine all device drivers in the Linux kernel will be rewritten in Rust. So it's a safe language. It's better than Cherry because, almost better probably, but it has type safety, spatial safety, and it actually in most cases has temporal safety, unless you use unsafe types and like you broke the lifetime rules somehow. But still, even if you rewrite in Rust, how many vulnerabilities are disappearing? What's your guess? What's the percentage of vulnerabilities? A lot. What is a lot in our world? Roughly speaking, 70%. And our study kind of matches the studies from Microsoft, which also did the same study for Microsoft Windows and other. If you just blindly rewrite your C code in Rust, that's what everyone wants to do now, roughly 70% of vulnerabilities are disappearing, which is a great deal. Like only 30 are left, but still 30 are left, and Cherry will be left with the same number, maybe even higher. And for these 70, they don't always eliminate the vulnerability completely, but sometimes they only reduce it from a full exploitation to like a denial of service. The Rust will still panic, roughly speaking, which is like still a huge deal because if you send a magic packet and the kernel crashes, that's not fun, right? Okay, so lack of revocation is probably a very bad thing in Cherry, and I don't think that it's possible to fix, like for real. My other philosophical observation is that, which is another weakness of Cherry, is that Cherry kind of pushes you to implement isolation at a very fine grain level, meaning that, like for example, Cherry is not against passing the linked list across. Like literally, like if everything is a capability with bounds, if you have a pointer to a linked list, and there's another pointer to the next, which also has bounds, and also has bounds, right? Cherry can say, look, move this pointer across and be happy. What's wrong with this, you think? What's the intuition? No?
Now you have access to like the entire.
That's a great observation. What if this data structure accidentally has a pointer to everything. Like you're right. So intuition is absolutely correct. It's very hard for us as humans to reason that you cannot accidentally pass a pointer which leads to a state which is private to you, or maybe like covers entire heap. Maybe in a linked list, it's kind of like hard to imagine, and a more realistic kind of a flow of passing a linked list that when you receive a, like imagine this linked list is passed inside function f. Well, this function f has very carefully validate what was passed. Maybe it didn't pass a linked list because Cherry doesn't care about types. Maybe they passed a tree, or a list with cycle, because you know attacker is so mean. If it's a list with cycle, you will be probably spinning here forever. And now, like every time you get a pointer, you have to think of it. Is it a list? Looks like a list. Is it circular? No, thanks God. Does it terminate or whatever? Maybe this one points to, like, maybe it's even different type, right? So maybe it's object A, object A, and this is B. Imagine how hard it will be to like enforce checks on the boundary. The more complex the data structure is, the more checks on the boundary. But in your case, like you can accidentally leak the entire heap. So, and it's almost like in Rust. And we, in this paper, which I was mentioning, Redleaf, we kind of looked at the same problem, but in Rust. And we came with a specific set of rules of what is allowed to pass and what is not. And despite the fact that we had Rust versus plain, you know, hardware capabilities, it was very, very hard, very, very fast, up to the point that we were saying that don't pass anything non-trivial. Otherwise, you immediately screw it. Although we did have a type set in Rust, if it compiles, I know for sure that it's a list. I don't know this circular checks are elided, so you still have to like make sure that you know you're not going to be spinning forever. But so essentially, at the sub level, like the observation here that you cannot be super duper fine grained because the semantics of those objects is so complex that you're probably introducing an infinite amount of vulnerabilities, or those are called cross interface vulnerabilities to begin with, right? So you have to be careful and you have to stop. But okay, hold on. So I have like a couple of minutes. Okay, that was my kind of brief introduction to Cherry. So you kind of got this. I talk about that revocation doesn't work. I kind of explain it on the board, but I wanted to like talk a little bit about performance, right? So we've seen this plot before. This is normalized to unsafe C, and like the first light green bar is NACL. NACL is Google Chrome, right? SFI pass, no hardware support. So not surprisingly, overhead is not horrible, but it's not great either. So next is MTE. MTE, well, remember, it still has the same bitmap instruction in front of every load and store. So it might help you sometimes, and sometimes maybe there might be a deficiency in our toolchain as well, but it's kind of sometimes it's like slower, who knows why. But it's still not fun. So roughly speaking, the same overhead. So because Jared, you asked about what's wrong with MTE. So reason number one, it's kind of the overhead sucks, right? Pack, which I didn't cover for the reasons that, okay, it just shoots through the roof. Like whoever wants to use Pack has to really be very, very careful, protect maybe some very simple and small pieces of code, because otherwise everything is like, how many, like 100% slower, right? So not fun. Okay, cool. Same on Intel. So we looked at ARM. ARM has a slightly different set of mechanisms. And here, this MPK scheme kind of like strikes you immediately that introduces almost no overhead. Why is that? Do you remember? Who can tell me? Yeah, you know. Anyway. Like, it's an easy question if you follow, but I know it's hard to follow. Like, how does MPK work? Correct. No, but wait, PKRU is a register on the CPU. So the checks are done in silicon, meaning that you don't need any kind of like a bit masking instruction in front of the load. this CAC is done in hardware, right? That's the big deal. So it turns out that the moment you introduce him in a single instruction, actually, by the way, our scheme with MPK does enforce control flow and shadow stack. Remember, otherwise it's laughable because if you have, remember I was saying that if you have a move instruction, but you jump in the middle of it, you get a write PKRU instruction. Just because that's how CPU interprets it, because if you start from here, it's write PKRU, right? And then you can change the fact, right? And I mentioned two solutions. One is to do the binary rewriting, finding those sequences, rewriting into equivalent sequences without write PKRU. People do it, right? It's and the second one was using hardware breakpoints, but ideally, you would like to avoid it as well in hardware. So and MPK doesn't do that, so we do CFI, so control flow enforcement. So meaning that you cannot jump in the middle of instruction. You only jump to where you're allowed to jump. But this is a powerful observation, so that any solution which pretends or like strives to be a hardware isolation solution should do this check in hardware. Because even if you introduce a single instruction and you cannot avoid this instruction in any of the software fault isolation paths, you're immediately sacrificing performance, right? So here's the comparison with Knuckle on Intel. So like that will suck. And here is the this third one is SAG is I don't want to talk about it. It's like a segment-based solution, so it's reasonably fast. But again, the thing which I was showing you last time is that majority of the SFI overhead. So here we have three overheads. So one is the registration of a register where we keep the tag or like bounce the control flow enforcement with a forward and shadow stack return masking, and then like those introducing negligible overhead. That's why our MPK totally produces 0.4 average overhead, 0.4% average overhead. But the majority of the overhead comes from this enforcing the bounds of accesses through this instruction, right? So, and I probably should stop here, but essentially I skipped a couple of mechanisms. One is like something called extended page table switching with VM-Func, which we used in our work, and a couple of probably the ones which are horrifically slow and not even usable. But this is kind of more or less the landscape of this isolation mechanisms. So if you didn't have a chance to read the paper, like the major characteristics are essentially overhead of enforcement. So, and I call it like hardware transparency, meaning that the isolation mechanism should not require you to like stick another instruction in front of every load and store. Then second is core coherent synchronization, and importantly, revocation of writes, because Cherry has only synchronization, but not revocation. And the third one, ideally, I don't have a name for it, but avoiding this second memory access. So if you have a large metadata in memory and you're doing a load operation from memory, ideally, you should not introduce the second load when you go and check the metadata table, because it will drop the performance of some of your workloads like database joins or metagenomic workloads where you do a lot of like data processing and looking up hash tables. Don't know anything about AI. Maybe AI people do the same. Maybe they also saturated, but that's also not the case. So that's kind of the reads out. And the other parts of this work, essentially, how fast you can cross. We're not going to talk about it much, but essentially, like there's still the challenge to get to the overhead of a function invocation, which is roughly like 3 to 5 cycles. But all of these, even if this mechanism, write PKRU takes literally 0 cycles. Like by the time you saved and restored registers, let me show you the slide. Like that's your like ideal. Man. Like this is the ideal primitive, which is magical in hardware on x86, but without extended registers. What I meant to say that it's non-trivial. By the time you saved and restored general and extended registers and picked a new stack, you already left, you lost, I don't think you lose 2022. That's maybe just with general registers, but you're gonna lose some cycles and some optimizations are required there as well. So, okay, let me stop here. So, because it was enough for now, right? I have a ton of other interesting slides, but we'll stop. And then we'll come back next week and we will probably, most likely, we will hear about this Redleaf. There are two options. Either I will explain how you introduce isolation in unsafe C code, the work which is called K-split, or we will talk about languages and listen how language isolation can be done, like how programming languages can be used for isolation. So one of these two, but I'll see you next week. Most likely the lecture will be either on Zoom or maybe even recorded in case I will be traveling, unfortunately, like physically, like being somewhere on that period of time. So maybe I will record it and post it.
Where you go? Where you go?
Where do I go? I go to Colorado to pick up my kid. She's doing a ski camp. So I just want to go and pick her up for Thanksgiving, essentially. Okay, so there's a chance I'm not going to see you. I'll send an email explicitly about my travel arrangements and recorded lectures, but please work on your projects because, okay, let's say last day of classes is a deadline. I can send them, like put an official deadline, but let's work on them. We don't have much time. I think we only have like 4 lectures left if we don't skip a single one. So I still want to teach a little because there's still some stuff which I wanted to talk about. Okay, thank you then. But then, yeah, if I don't see you, then have a happy Thanksgiving.
Well, we come back.
I like after Thanksgiving, I definitely will be here. But the week of Thanksgiving,
Next week.
most likely I'm not in person. I might not be even live, but I will record lectures and post them online so you can watch them